Welcome to Uptime project webinar. I am Michelle Giordano and I work as Communication and Dissemination Manager for RINA. So today I'm going to present you Uptime project webinar, and in particular we are going to talk about Uptime innovative solutions and focus on Whirlpool business case. So we are going to show you the fundamental steps for a data-driven strategy and show you a live demonstration of Uptime platform. So thanks to also the participation of Whirlpool, we are going to introduce you to the lesson learned in the framework of Uptime project and show you the best practices to approach a predictive maintenance project, in particular applied to the white good industry sector. At the end of the webinar, there will be a 20 minutes Q&A session. So as you can see, you have a GoToWebinar panel on the right if you didn't move it in other parts of your screen. And through the GoToWebinar panel, there is also a section dedicated to questions. And you can use the questions panel to make questions, and at the end of the webinar during the Q&A session I will read your questions out loud for you so that our Uptime experts can answer to your doubts and curiosities about the project. If you have some technical problems or you don't know how to use the question panels, please use the chat to warn us, and we will support you in showing how to use it to make questions. So today we have in particular three main speakers, and I would like to thank Mr. Petrali, Mr. Barbieri, and Mrs. Lampataki to be here with us today to talk about our project. And in particular, I would like now to introduce a little bit them to all of you. So, Mr. Petrali presently coordinates manufacturing, research and development activities for the EMEA region. He is the head of manufacturing for the research and development activities for Whirlpool Corporation. And he is directly involved as a technical and main partner in more than 10 founded research projects in the last 5 years. And moreover, is currently working in the definition and implementation of Whirlpool Industry 4.0 strategy. Moreover, he is also the inventor of 5 patents and the author of several technical papers, mainly related to technology forecasting, manufacturing quality, Internet of Things, and Industry 4.0. So thank you, Pierluigi, to be with us today. And then we have also Mr. Manuele Barbieri presenting, who is actually my colleague and the principal consultant at RINA Consulting. In particular, Mr. Barbieri has been involved in several safety and security projects for risk analysis, specification of requirements, and design of countermeasures and mechanisms for hardware and software processing sensitive data. And in particular, in the framework of Uptime project, Mr. Barbieri acts as the technical coordinator for RINA, following the development of failure mode and defect criticality analysis tool and the validation of Uptime platform. So thank you again, Manuele, to present the project today. And last but not least, we have also Mrs. Fenaretti Lampataki, who is the technical coordinator and among the co-founders of Suite 5 Data Intelligence Solutions Limited. During the last 15 years, she has successfully led the team's research and management activities in a series of funded projects, in particular related to data interoperability, big data analytics, and artificial intelligence. Her research results have appeared in over 75 publications in international journals and conference proceedings, and moreover, she's also co-edited one book. So thank you very much, Senareti, to be with us. And now I would like to leave the floor to my colleague Manuele Barberi, who will introduce you to Uptime solution. Thank you very much again and welcome to our webinar.
So thank you, Michelle. Hello, good morning to everybody. So I give you some information about the project. The international consortium is composed by end user, FFT, Whirlpool, and Maillis, technology provider, BIBA, UBTech, SCCS, Suite 5, Pumacy, and Rina Consulting, and Innovation Management, Muse and Isadeus. Uptime is an innovation action project submitted under the European Research and Development call Factory of the Future, and has a duration of 36 months. The project will end at the end of August of this year. The main objective of the project is to reframe. Next, please. Is to reframe the concept of predictive maintenance in a unified way, exploiting technological advantage in three main areas: Industry 4.0, using sensor, big data processing, processing real-time and batch data, and proactive computing, mitigating undesired events by making prediction and supporting the user in taking decision. Next slide, please. The Uptime integrated platform for predictive maintenance is composed by 7 components: the Uptime Sense, that acquire data from sensor; Uptime Detect and Uptime Predict, that detect and predict the state of the system; Uptime Decide, that proactively recommend maintenance action; Uptime Visualize, that aggregate and visualize data; Uptime Mecha, that provide failure mode, effect, and criticality; and Uptime Analyze, that make prediction on the basis of analysis of historical data coming and stored in the legacy system. The interoperability of the solution has been considered since the beginning of the project by designing the platform in accordance with standard, using model and exploring ontology relevant in the maintenance and Industry 4.0 domain. Next, please. Yes. Here we have some screenshot of the Uptime integrated platform that will be presented in the demo. From the left side, we have a dashboard view with a graphical representation of the Uptime system deployed in the steel industry business case. In the middle, we have the batch data analytics view that predict future possible interruption using insight such as maintenance log and OEE data. In the right part, we have the decision-making view that proactively recommend maintenance action. Next slide, please. The Uptime integrated platform has been deployed in 3 business cases: white good appliance, steel industry, and construction and of production system. The white good appliance use case deal with complex automatic production line to produce drums for dryer. The equipment, as we'll see later in a dedicated presentation, is a sequence of different steps involving many operations and requiring the synchronized action of mechanical, electrical, hydraulic, and pneumatic tools. The steel industry use case deal with cold rolling mill for the production of steel strapping. Cold rolling is a process of reducing of the cross-sectional area through the deformation caused by a pair of rotating metal rods. The use case of FT deal with the maintenance of manufacturing equipment within the aviation sector. FFT hosting equipment comprise a transportation jig used to move aircraft component wings during the assembly of an airframe. Now I leave the floor to Pierluigi.
Good morning, everybody. I will show even the context and how Whirlpool prepared the use case for this project. Okay, couple of words about Whirlpool. Whirlpool is the major domestic appliance manufacturer in the world, with more than 21 billion sales in last year, and employing more than 92,000 employees in the world. Of course, Whirlpool is present almost in every continent, but he has a strong presence in the European region, since we are hosting the European, Middle East, and Africa headquarters here in Italy, and we have factories in Poland, in Italy, in England, in Turkey, in Slovak Republic. Also, we are a member of World Class Manufacturing Association, because world class manufacturing is actually the way that we are using to improve our operation. Next slide, please. That's actually a very brief and short description on what world class manufacturing is. Is recognized in the word methodology for continuous improvement in the factory. So, and of course, it has a lot of different pillars to lay on. Many of those pillars are something to do with maintenance. So maintenance is very important for keeping our production system health and providing values. Among those pillars, next slide, please. There are 3 of them. Next slide. 3 of them are very important for maintenance. So maintenance has not be considered just for the last part, the professional maintenance, but maintenance has to be built somehow in the workplace itself, with autonomous maintenance, with the responsibility of operators for doing basic operation. Of course, has to also take into account the design of the machine itself. So the early equipment management tells us how to design, commission, install, and test the machine so that they could be actually maintainable in the future. But of course, the most important pillar for world-class manufacturing is professional maintenance. Next slide, please. What is the objective of professional maintenance according to world-class manufacturing? If, of course, to keeping and machines equipment efficient enough by eliminating breakdowns and reducing component replacement frequency, which is mean actually reduce cost. The need is, of course, to make sure that our equipment is always there to produce at the right time, the right part, so without defects, at the right cost. And of course, the objective is to have 0 breakdowns, so machine working without any break during their availability time, but also to increase the technical availability, so to have the machine works for more if needed. And most important, reduction of maintenance cost. Next slide, please. Every pillar in world-class manufacturing is divided into 7 steps. Those are a description of 7 sequential activities to reach the excellence. As you can see, broadly speaking, we can divide these 7 steps into 3 phases. One phase which is reactive, and for maintenance is of course react to something which is happening. The machine is broken and the maintenance is doing something. Then there is the preventive approach, in which I can do something beforehand it happening, but just based on experience, just based on scheduled activities. The most evolved steps is, of course, the proactive. And the proactive part is exactly the step 6 of professional maintenance pillar, and is here prescribing a way to build a predictive maintenance system. So this is to tell all you attendees that preventive maintenance, predictive maintenance can't be simply built over the desert. So we need to have a continuous improvement of our organization, skills, process, procedures, and so on, so that it can be applied in the most efficient and effective way. Next slide, please. So predictive maintenance is just one of the potential maintenance type that we can have. The most common one is breakdown maintenance, reactive. So act when the machine is broken. Actually, predictive maintenance is something that it requires a lot of efforts, a lot of technicalities, a lot of skills, and not all the machines. You can decide where to apply or where it's convenient to apply different kind of maintenance. For machines which are not in the critical path, for those who are producing parts which are not a big value, sometimes breakdown maintenance is also the one that can be applied. However, for machine which is very important, the one that are providing more value to your factory, the one that which are the most important part of losses, so classified as a AA or A, of course, the amount of time-based maintenance, which is preventive maintenance, and condition or corrective maintenance, which is actually the predictive, has to take more than half of the mix. So that's important to choose the right machine and the right way to implement predictive maintenance. Next slide, please. Which are the objectives? Of course, with predictive maintenance, we are expecting to improve the efficiency. Through what? Through the reduction of mean time to repair and to the improvement of the mean time between failure. But most important, predictive maintenance can work on another important KPI, which is reduction of total cost of maintenance. Next slide, please. We provided to Uptime project a use case which is based on a quite complex production line based in our factory in Łódź in Poland that has been installed in the first quarter of 2019, has been becoming operating a full regime at the end of the same year. It's automatic production line, which starting from a coil of steel, after many different stations, straightening the coil till punching, seaming it, flanging, making some assembly, arrives to produce the internal drum where you have to put the clothes in your clothes dryer. So quite a complex machine. We decided to concentrate the study on some of the workstation. Not all the workstation has been involved, but of course the machine has to be considered in its entirety. In the next picture, if you can scroll the presentation, you can see some of the shot of the machine itself, just to let you understand the dimension and the complexity, the amount of different actuator sensors that are over there. So it's really a complex machine and quite a big one. Okay, so the status before Uptime for the maintenance was, of course, we were not yet at step 6 of the professional maintenance pillar. What we were something between 4 and 5. So all our activities for maintenance were reactive maintenance, of course, and some preventive. The preventive maintenance were done according to what we call the equipment ledger, which is simply a list of all the components of the machine. And for each component, there is a prescription of where the components has to be checked or substituted. So those was our initial point of view, and that's what we started working on in Uptime project. Now I left the floor to Fenareti and Emanuele that will describe how Uptime implemented the Whirlpool case, and will provide you also a live demonstration of the platform itself.
Good morning from my side as well. In the next minutes, we will see how the Uptime platform has been adapted to the needs of the Whirlpool business case. And starting from the architecture, you can see on the left side of this figure how different sources of data, ranging from sensor data that have been installed in the factory to legacy and operational data that come from different systems that are available in the factory, have been leveraged in order to create certain predictions in the direction of predictive maintenance. The sensor data have been processed at real time through the Uptime Sense, Detect, Predict, and Decide components. The operational and legacy data have been analyzed through the Uptime Analyze component and have been also leveraged in the Uptime Mecha component. All the results of the analysis that has been performed in terms of recommendations, in terms of predictions, in terms of monitoring what is happening in the factory have been visualized through appropriate interfaces with the help of the Uptime Visualize component. The Uptime platform is intended to be used in the specific business case by different maintenance managers, but also by factory workers that should have readily available notifications with regard to the actions that should be taken. This is the overall picture of the Uptime platform in the Whirlpool business case that was gradually delivered in different iterations. In order to deliver such an architecture and bring together the whole vision of how predictive maintenance should be implemented, there were certain fundamental steps that needed to be taken while the equipment was installed, tested, and started working in the factory, as Pierluigi explained earlier. Our activities were structured in two parallel streams. The first one was related to how we will leverage the knowledge that existed from historical data in order to understand how the production line actually works. And this part of the analysis from the historical data has been afterwards complemented by actual operational data that have been analyzed and are continuously analyzed. The second stream of data started with a FMEC analysis, a failure mode effects and criticality analysis on the different machines based on the past experience from different factories on the drum production line in order to understand for each and every machine what are the critical features that should be taken into account in order to decide what are the new sensors that should be installed on the different machines in the production line, as Pierluigi also explained earlier, and in order to explain in a reasonable manner what are the machines that should be prioritized. In the end of the day, we ended up having data, sensor data from two high-level different sources. On the one hand, we have what we call part gauge product measurements that are analyzed, and we continuously learn from the patterns and the anomalies we detect. And on the other hand, we have what we call equipment gauge measurements on the machines that are also utilized in order to early detect certain anomalies on the machines themselves. All these results from the historical, operational, and sensor data come together because we came to realize very early from the implementation of the activities in the Uptime platform that one of these individual analyses would not solve the problem. We needed to bring all the wealth of data we had at our disposal together in order to understand what are the actions and predict what are the actions that should be taken again through a plethora of descriptive, predictive, and prescriptive analytics that we have applied in the Uptime project. In the end of the day, the intention has been to integrate the results of the analysis that we have performed and all the inner workings of the Uptime platform in the maintenance business processes of Whirlpool. Next slide, please. We will start with looking into detail on how the historical and operational data analysis worked. So next slide, please. In this case, I will just take one moment to explain you the different sources of data we had at our disposal, starting from the maintenance ledger that captured a wealth of information related to the machines and the typical maintenance actions that are recorded, the operational data either stored in a database or complemented by the workers in the factory. But also what I would like to underline is that since the factory was new, we had at our disposal certain historical data around maintenance that came from other factories of Whirlpool in order to help us better understand how the analysis, what results of the analysis we could derive and what are the patterns and the rules that we could identify very easily. And to this end, we utilized a number of machine learning and deep learning techniques in order to derive results. And at this point, in the next minutes, we will see a demo of one of the components, individual components of the Uptime platform, that is the Uptime Analyze component. We can see the different data sets that have been uploaded in the platform. Very quickly, I'm not sure if the video is on, Michelle. Okay. We can upload very quickly a data set by selecting the name, the team, the factory it refers to, the production line, provide a very quick description and upload the file in a CSV format. In the next step, upon filling in these basic metadata, a semi-automatic mapping based on fuzzy matching techniques is performed between the source columns of the data that are uploaded to the equivalent uptime concepts in the predictive maintenance data model we have defined in Uptime based on different predictive maintenance standards. The user can correct anything that he feels or she feels that is wrong, and then a brief reference is made that different cleaning and normalization rules are applied. Looking at certain data sets that have been already uploaded, we can quickly load a certain data set and have an overview of the data and an exploratory data analysis to see the mean values, min max values, but also to look into the details of the data. So we can select from the data set we have at our disposal certain features, certain parts of the data we would like to visualize, like the interruption categories, the interruption duration, label them per theme or in any way we want, and we can zoom in, zoom out in the diagram in order to see the actual data. This is the preparatory step that helps someone that is not familiar with the data to better understand them. Then, upon a certain analysis that has been performed on the system, one can quickly see certain descriptive analytics in terms of some summary statistics that are calculated on the top, but also different interactive diagrams that depict the performance timeline, the performance overall, and we can easily notice that the planned downtime is far higher than the unplanned downtime. We can see the top 10 interruptions, failures, least interruptions per machine. We have the details of all the interruptions per machine. We can see a timeline of the daily events that happened in the factory and the timeline of the mean time between failures and the mean time to repair, the different types of interruptions per machine, the actual downtime per day, per week, per month. And again, we can easily notice that the actual downtime in very few days is higher than the planned maintenance time, which is very good for the factory, of course. And then we can move to the part of the predictive analytics we have performed in order to predict whether there will be a breakdown tomorrow based on today's production features, when we expect the next interruption, in how many days this is expected. Then we can move on to another type of analysis performed in order to indicate what is the expected interruption duration for the next days. Next day, for every diagram, someone can download the diagrams, etc. We can see what are the common features that days with breakdown exhibit, as well as the causes of interruption that are somehow related. And in the last analysis that was performed, we can see the different causes of interruption per machine. This was a very quick view of the uptime analyze component, and then we are going to move forward after having a glimpse at the historical and operational data analysis, how it works, on how the sensor data come to the foreground, starting from the preliminary steps that was the MECA analysis. And at this point, I would like to give the floor to Manuele to explain us step by step how MECA worked.
Okay. Okay. Thank you very much. Yes, the FMECA. Next slide, please. Is a systematic methodology to compute risk on the basis of failure mode of the failure and the impact on production and cost. Not only production and cost, but also safety, environment, and reputation. Each risk priority number associated to a specific failure mode is a function of the severity of the event, its probability of occurrence, and also the detection. And this detection is due to mitigation measure. Next slides, please. The uptime FMECA go beyond the state of the art, including the analysis, introducing simplified modeling to provide insight to the prediction part, and including the analysis of human error. Next slide, please. Why performance of FMECA? Besides traditional benefit associated to FMECA, such as an increased reliability, safety, and quality, introducing the FMECA in the operational phase of the system, we can evaluate the risk of failure during the entire system life cycle. And we can update also the FMECA parameters with information measured on the field in order to create dedicated statistics about failure. Next slide, please. As Fenareti previously said, one of the objectives of FMECA is to address the monitoring of physical parameter by means of sensor in order to detect specific failure mode. FMECA workshop conducted in March 2019 has been used to identify sensor to apply to some machine in order to detect anomalies linked to failure cause. So next slide, please. Yes, after the installation of the sensor on the decoration press, a press model has been created considering both data coming from the new sensor and also data coming from the existing PLC. The resulting model, based on the worsening coefficient, can be used to provide insight to associate anomaly to possible failure mode. Now I leave the floor to Fenaretti.
So upon seeing the rationale behind the new sensor installation, we will see now how the different sensor data coming from product measurements and the machines, how they were brought together in order to lead to certain predictions related to predictive maintenance. At this point, we will have, before this, excuse me, Michelle, we should see one slide. The next slide, please. And then we will move to the video.
There's a bit of delay, but you should see the slide now, Finaretti.
Thanks. I'm still seeing the previous one, but it doesn't matter. The target we have through the sensor data analysis and in general through all the different sources of data analysis we performed was to try to predict failures. I think one slide more, Michelle, with the one with the data map. Okay, no. Afterwards, this slide, and then we will go back to the video. We needed to predict the failures that will appear in the production line in the near future, 1 or 2 days earlier. As mentioned, the legacy and operational data related to OEE and the maintenance log has been already utilized in order to predict the breakdown for the next day or when the next breakdown is expected. The different part measurements related to concentricity, planarity, depth, and the equipment measurement related to pressure sensors, vibration, frequency, etc. They were all used to detect anomalies, to classify the different measurements we found and try to predict whether a certain defective product indicates a problem in the machine. This was one of the interesting findings we had because we saw certain correlations through the data. In the end of the day, the outcome was always to try to extract knowledge in a manner that would be actionable and understandable by the end user. So the type of rules we created internally was something like, if we have this type of measurements in a row, we will have a defective product in the next 4 hours that indicates this type of machine failure. Or if we overcome this type of threshold in a machine, we will have a failure in a day. And this type of predictions led to certain prescriptions that we provide to the involved people through the Uptime platform and the mobile app we have defined in order to communicate the findings to the workers and collect the respective actions that were taken. If we can go back to the videos, the first video first of the platform. Thank you. We can see the overview of the Uptime platform. On the left side that you can see the menu, you can see references to the different Uptime components, stream data analytics, batch data analytics, decision making. In the home page, we can see the overview of the production line and a timeline of the average of sensor measurements per hour. These are just some indicative data coming from the factory test data. The batch data analytics is something that we saw earlier, so we will not dive into detail on that. What we will focus is how the different sensor data have been utilized to identify and detect anomalies. For example, in one of the sensors, we can see here, we can see the anomalies detected with the moving average, and certain anomalies can be found in early February for pressure sensor 2 as well, or for with regard to the correlations between the defective products. We managed to predict if there is going to be a defective product that indicates machine failures in the next 4 hours and how many such defective products are expected to be found. And this type of predictions have been sent to the Uptime Decide module in order to evaluate them and identify through a reinforcement learning approach whether certain prescriptions, certain actions, recommendations for actions should be proposed to the maintenance managers. As you can see here, there is a list of different actions that can be taken. The maintenance manager can decide whether to approve, reject, or mark as completed a certain action. The visualization part is just to indicate the different actions and how they are all related. And after all these actions and the prescriptions have been created, what happens afterwards, how a worker can utilize this type of actions. This is why we have created a mobile application in which the worker should install in his mobile phone. He should always log in to the platform, to the application, obviously, and as soon as the worker is logged in the application, he can view or receive notifications for the recommendations provided by the Uptime platform, the date issued, the expected action date, the action description, the machine it refers to, and he can add new actions related to autonomous maintenance that were actually taken on the factory, the duration of the action and a short description, and this action is fed back to the Uptime platform in order to improve the future prescriptions that are made by allowing the system to always learn by the actual actions that were taken. If we go to the next slide, please. In the end of the day, all the analysis that we performed, we tried to find a way in order to communicate the respective recommendations and actions and consider how all these could be integrated in the maintenance business process in the Whirlpool factory. This created a lot of lessons learned and a lot of findings that Pierluigi will explain us in the next moments.
Thank you, Feneretti. Thank you, Emanuele. Yes, it's important to underline that this is a research project, so it's not an implementation project. And of course, one of the main outcomes of our research projects is to learn something. That's very important for companies. We had got a very deep learning on within Uptime. And I try here to summarize, and in the next slide I will get some advice point by point. The first is, of course, about data. Data is the basic foundation for predictive maintenance, and of course it's important to have a quality data set. What is mean quality data set? It's meaning that data has to be valid, has to be consistent, has to be representative of the physical process that we want to monitoring. Also, they have to be easily accessible. So find a way to put them in the right place with the right availability. And also, it's important to have the data always well documented, well described, because we cannot rely on simply involving every time the Excel to describe what the meaning of a column on a database is. Second important learning, quality is not enough. Sometimes also quantity is mandatory to have. This is especially true for those processes that are stable. I mean, in all our factories, maybe it's a machine, an equipment is there since years. And of course, after many years of operation for known processes, the failure rate is not that high, meaning that maybe we have a failure one each month. And so it's important to have high quantity data set. Sometimes is for making some machine learning, months are needed, sometimes also more than 12 months, so years of data. So it's very important if you want to start a predictive maintenance project to start in advance and start gathering data as soon as possible. Third big learning that we have, data scientists, I mean, expert in data architecture, expert in algorithms, and expert in processes are not communicating that easy. They are not having the same language. They are not having the same understanding of each own or each other domain. And so it's very important for them to work side by side as soon as possible. We need to find ways for them to share their knowledge, to share the experience, to find also a common ground where to exchange this kind of information. Fourth big families of learning. It's not just a matter of technology. I could have the perfect prediction which is going to be success 100%, but if the organization behind it is not able to look at this data, to trust on this data, to work on this prescription, and actually to move some advertisement or advice to practice, the business return is not there. So it's very important that we companies need to work and improve the skill of our people so that they can actually work more and more and better with the data and with this new intelligent machine that we will have definitely in our hands in very few years. In the next slide, I tried to just highlight it point by point what I tried to summarize in the first slide of this family. So right data to be used, yes. FMECA is a powerful tool because it allows us to focus on the component that will provide more value when interested in predictive maintenance. So it's not worthwhile maybe to put predictive maintenance on a very low value component, which is not going to fail so often, and maybe that has a very, very low value of replacement. While on the opposite is better to focus on those components that are high value, difficult to be replaced, and so on. Second advice, act in advance. As I said, sometimes we require many months or years of data. So as soon as possible, if you have in mind to run a predictive maintenance project, start to make a start to place sensor and to gather data. Maybe for the first 6 months, they will not provide any value, but after 6 months, they can be used to make some interesting machine learning and make some prediction. Third advice, define a standard and semantic data model. It's very important to shorten the time that is used by people to exchange the meaning of the data. And we experience in Uptime many times, many meetings to just explain how the data, a specific set of data were the meaning of them, and were not possible to focus correctly on it as soon as possible. So that's important to have a way of defining metadata and to design the data architecture as well as possible. Also, the infrastructure is very important. The more the data can flow without any problem, without any technical problem also, between the sensor to the storage where the analysis has to be done, the better it is. So it's very important. Nowadays, there are a lot of platforms available on the market, but it's very important that companies establish as soon as possible the right architecture in order to make this data flow and be correlatable to other data in the most efficient way as possible. Correlate data is another interesting thing. The data itself is not representing anything. Every time we need to correlate this data with the time or the status of the machine or the status of the production or something else. So it's very important to make sure that all the time a data is generated is being correlated with something else. About process expert and data scientist, also here the advice is to start defining as soon as possible a way for them to work together. I would suggest to close them in a room for 3 or 4 weeks and then lock them down and open just after 3 months. But of course, this is not possible, especially in this period. So we need to find a way for them to work, share as much as possible their experience and provide all the documentation. It's a huge work, but it's really worthwhile. Okay, prediction. Prediction must gain expert trust. So one of the important risk, the higher risk in prediction is that the prediction is even too low, so we generate false positive, or too high, we generate false negative. We are not generating negatives when there are. It's a learning stage. That's why we need to iteratively work with experts so that they can find the right algorithm, find the right correlation of data, and find the right prediction model. It's very important because, of course, if operation technology people is not involved in this process, they can be simply exposed to the initial solution and they can simply say, okay, the system is not working, and the risk that an overall predictive maintenance project is not providing any value is very high. Last point, as I said, organization. We are not just talking about technology. Here, we are talking about the way in which people are using some decision, some suggestion generated by a machine. So it's important that our people in the factories will start increasing their skills in dealing with data. They need to recognize the importance of making decisions based on data. That's not that easy, but is a mandatory. I mean, we cannot have a perfect prediction machine if the people that should take this output is not able to read it. And with that, I finish my speak. I asked for the question and answer session now, so I'll leave the floor to Michelle that will moderate the question and answer.
Yes, thank you very much, Pierluigi, Manuele, and Fenareti for your presentation. Now it's Q&A time, so please, participants, you can use your question panels, and if you have some troubles in using it, please use the chat to warming. Actually, we have already 2 questions. So first question, how predictive maintenance impact the economic returns of the company? Maybe Pierluigi, you would like to answer to this one.
Yes, absolutely. Let's start from the starting point is to have a machine which is already close to zero breakdown because we are implemented a very strict preventive plan. So we can actually, with the tool that we have today, have a machine which are close to zero breakdown. Let's just make an example. On our cars, if I'm doing correctly all the check, if I'm going to substitute consumables, oil, and so on, more than requested by the preventive maintenance, I can pretty sure that my machine is going to not to break anymore. Of course, this is a cost because substituting the oil every year could cost a lot. Go to mechanics to have some checks, it costs. That's where predictive maintenance can actually jump in. It's not needed to substitute the oil just based on a time-based plan. but I need to substitute the oil before it is going to be dangerous. And that's true for all the components. So the role of the predictive maintenance is to modulate the preventive action that has been already planned, so to, in one way, reduce some intervention. So I can avoid to substitute a component, maybe it's a cost component, because the machine is telling me, yes, this component is still in a health situation, so you can wait to substitute it. Or it can telling me, look, I know that your plan to substitute it, it will be acting in 1 month, but the sensor are telling me that this component is not behaving well. So it's better for you to substitute it in 2 weeks. And so in this case, I can avoid a breakdown. So those are the two levers that predictive maintenance can work. Modulate the preventive plan so that I can anticipate some intervention. And this is also, it has another important source. This imagine to have the spare parts of my equipment that can be actually reduced to a minimum, because I can maybe order very cumbersome or very expensive components, not 1 year before, but just 2 days before I need the substitution. So it is also a reduction of my warehouse. Or on the opposite, where my preventive plan is not enough to improve the efficiency, I can trust on predictive maintenance to avoid some potential breakdown that can occur, and the prediction is able to tell me, please go do something because the machine is going to be fail in 2 weeks. Those are the two main part. Of course, it has the economic advantage has somehow considered in terms of the cost of maintenance. Probably it doesn't make any sense to have a prediction management system which is cost 100,000 a year if the components to be substituted is costing 1,000 euros. It's for sure more economical to substitute the components 5 times a year and not having any predictive maintenance in place. So the economic value needs always to be evaluated correctly. We are not here to just make projects, and the Industry 4.0 is not for the sake of technology, so for the sake of producing business results. I hope I've answered.
Yes, thank you very much. We have actually several questions here. So the second one, which is linked to another one who just arrived, is what was the total number of sensors installed on the case study line? And please, could you please provide examples of sensors that were placed in the line?
I also think the machine were already equipped with some sensor to measure the quality of the part. This before the project were starting. So we had a vision system able to measure some parameters of the drum line. Sorry, the drum, the planarity of the drum itself, the depth of the drum, and other measure related to the components. Then we worked together with the supplier of the machine, and they actually identified a vibration sensor and pressure sensor to be placed in a specific part. We are talking about let's more or less is less than 8 or 10 added sensor afterwards. So FMECA, the process of running the FMECA were suggesting us to add the temp sensor, and we are talking about vibration and pressure sensor in this case.
Okay, so we thank you very much, Pierluigi. We have a third question, which is what kind of algorithms are used for the failure prediction? Do you use neuronal networks or a supervised learning method for the deep learning process for pattern recognition, which allow the prediction of potential failures? So maybe that's one is Fenaretti, who can
This one, yes, this one is for me. We have actually utilized a number of algorithms. We have utilized neural networks, we have utilized LSTM, we have utilized regression, decision trees, and this category of algorithms. It was always depending on the data we had at our disposal, we decided what algorithm exactly we should use and what was the one that brought the best results. So the results that you have seen so far, they come from a different set of algorithms each time.
Okay. So we have maybe another question, which is actually always for you, Fenaretti. Is it possible to have more details about the prediction tool and the prediction of the next failures in the next 3 days?
Yes. In this case, the prediction that has been provided is again something that came out of the experimentation. The time frame of the predictions was something we utilized the next day. We utilized the predictions for the next day, for the next 5 days, for the next 10 days, and we realized that the prediction for the next day was the one that provided the most accurate results instead of a larger time window. And the reason for that was the actual data we had at our disposal. When it comes to the sensor data, this was for the operational data we have. When it comes to the sensor data, the time frame of the predictions is again 4 hours to 1 day. The 4-hour window that I mentioned provided better results than a larger time window. As more data come, we're still experimenting with the algorithms, to be honest, because it is something that it is not, let's say, written in stone, the results that we have yielded so far. And as we get even more data, we're still experimenting with the best time window for the predictions we make. At the moment, though, what I would say is that we are not yet to the 3 days for sure prediction window. We are trying to predict certain things, and we have also experimented with more predictions that you didn't see at all. For example, try to predict the next anomaly on the machine measurements, and this is something that did not produce successful results so far. The predictions for the next failure, when it is expected and what is the duration, and the correlation between the prediction of the next default products that are related to machine failures, these are the ones that we got the most satisfactory results so far. What is worth mentioning is also that from the initial analysis we had, certain algorithms were overfitting the data we had, so we had to change. Apart from introducing next data, more data that came afterwards, we had to fine-tune certain things, because some of the results we got that you didn't see, of course, right now, especially the prediction for the next day, was too good to be true. But we came to realize very quickly how we should fine-tune all the features we included in the algorithm in order to better predict non-anticipated situations in the future for which the model was not initially trained for.
Okay, thank you, Fenariti. We have another question, and I guess it is again for Pierluigi, who maybe can also turn on his camera if it's possible. So the question is, what is the expected return of investment of such a solution in production? So it is actually related to the first one, but.
Of course, this calculation has not yet been done. Because of course, being a research project, we don't know actually how the system could be evaluated commercially. So we don't know how the Uptime platform overall could be costing to a company yearly. This is something that will be done probably in the next phase of the project. But as I said before, the way to calculate the return is pretty easy. I mean, the cost of maintenance is there. And if you can predict that some specific action of predictive maintenance could impact on most important expenses of the total cost of maintenance, which are components, the storage of components, the amount of time used by maintenance to repair it, the total amount of losses due to unavailability to break down the machine, those can be easily calculated. And of course, I cannot disclose here the cost of the maintenance of our machine because it's sensitive data, but it's very easy. As soon as we have we will have the some indication on how the uptime commercially available could cost to a company, will be very easy to make a business case.
Okay, thank
you. As I said before, it's quite easy to compute, and of course has not to be used everywhere. Also, if you remember in my first slide, the world-class manufacturing itself is suggesting to address advanced maintenance approaches, predictive, proactive, and so on, for critical machine, which are AA and A. Critical machine are the one that are, if you calculate all the losses, economic losses attributable to machine, the AA are those which are constituting 50% of the losses. So a machine which is costing me 30,000 euro a year for maintenance, which is something that could be easily achievable in a quite complex machine, the calculation is easily done. If I have a system which is able to cost less than 30,000 euro a year, it will provide some positive return. Very thumb rule, but of course, I mean, anybody has some its own way to calculate business cases.
Okay, thanks you very much. We have another questions, which is what kind of communication protocols material did you use to collect the data from the machines to the cloud? And maybe Fenareti can answer to this one.
Sorry, Michelle, could you please repeat the question because there
Yes.
was some interruption.
Yes, I know there are some delays, unfortunately, in the webinar, so I will repeat it. What kind of communication protocols material did you use to collect the data from machines to clouds?
Okay, the sensor data in the sensors that were installed in the factory communicated all the data to a PLC that was stored, that was in the production line in the factory, and the data from the PLC, they are forwarded to a local database that we're utilizing then to Uptime.
Okay. And we have.
Maybe I can add something here,
yes, of course.
Michelle. Yes, this is, of course, has been done for keeping, or better, not disturbing too much the line in production. So the option to have the new sensor feeding directly the Uptime platform was considered a little bit too risky for the time being. So that's why we decided to use the existing mechanism, so to convey all the new sensor data to the existing PLC to the machine, and then feed the Uptime database. To be very honest, this is good for what is regarding research project, but we realize that it's not what we need to have for production. So what we are planning to do for next implementation is to actually take the sense or Uptime module and to connect directly to the sensor, maybe. And I think we are going to evaluate for sure some standard protocol like OPC UA and MQTT. We are not yet at that decision, but for sure what the learning that we had is that the architecture need to be lean also. So not only the automaton, but the architecture need to be lean enough to ensure that all the data are going without any further manipulation between sensor and to the database. And of course, we are also evaluating Influx DB as a potential database to be used for storing this kind of data. That's for the future, of course.
Okay, thanks. We have one more question, which is, can you give few examples of performance you obtain? For example, percentage of anomaly detected or percentage of false alert? Yeah, that's a difficult one. I can see it
Yes.
from your face.
In order to have a right question, I mean a right answer on this question, we should have some month of working of the system. So we are not yet there. We need to collect many more data and evaluate the prediction with the reality, which is the best things to do. I mean, the prediction has been, the final algorithm has been tuned up some weeks ago. So what now we need to do is to run in parallel the prediction with the real production and see how many prediction are actually representing then the reality. So we are not yet there. I think we will be there for sure for the end of the project that is foreseen by the end of August. And so by the end of this period, we can be for sure able to provide any further detail on quantitative results of those false positive and false negative.
Yes, as you mentioned, the project is not over yet. So after the Q&A session, I will show you how to be in touch with us. So maybe the answers the questions that we didn't answer today will be answered in the next months. So for now, we don't have any other questions, but maybe I would like to give you still a couple of minutes to reflect on the contents we show you, and maybe you will have some other questions. And in the meantime, we have also our project coordinator connected, who is Yves Keraton from Isadeus company. And I don't know if he maybe would like to add something, or just to, I don't know, say something about the project as the coordinator.
Yes, thank you, Michelle. Actually, I am not the coordinator. I am just taking care of standardization aspects.
Okay, so
just to mention, maybe to add something to what Pierluigi highlighted about the use of standard protocols for the data. He mentioned OPC-UA and MQTT, which are standards we have identified as standards to be used, but as you said, for the future. If I can say some words about standardization strategy we had, it is an integration strategy, so we follow the, or to say, the innovation work of the team, and from the beginning of the project we identify standards. There are many standards from ISO, AEC, and other standardization bodies. So we listed these standards, and we use a chart, radar chart of the standards, which is a powerful methodology used in the aerospace industry, for instance, for an ecosystems to identify the standards to be used, to be followed, or to be part of the making or participating to new revision of these standards. And as was also mentioned by Manuele, yes, we are following, of course, the ISO 13374 about the condition monitoring and diagnostics of machine systems for data processing, communication, presentation. And also we use the MIMOSA condition-based maintenance schema. Fenretti has shown some mapping from models of the historical database to the Uptime data model, which is based on this MIMOSA CBM schema. So just if I can add a last word, Manuele mentioned also we explored the possible use of ontologies for an extended intro all the components and between the components of the Uptime platform with the information system of industries, but it's how to say, it's more a research topic also. We work on terminology with inside a cluster of 6 H2020 project of about predictive maintenance. So we make efforts to define a common terminology, to have this standard for semantic data model mentioned by Pierluigi.
Sorry, Yves, some participants
kinds
asked
of terminology, but also I think we have to.
Yes, some participants
Excuse
asked us
me?
if you can repeat the number of the ISO used, the number of the ISO for predictive maintenance.
It's ISO 13374. There is several parts. It's ISO 13374. Okay. And it's about, the name is condition monitoring and diagnostics of machine systems, data processing, communication, and presentation. And for instance, yes, we have different functionalities which are specified for predictive maintenance system, and the Uptime solution is strictly following this these different functionalities.
Okay, thank you very much.
What is sometimes unusual in a okay, it's that the MIMOSA CBM schema is mentioned in the ISO standard as a correct implementation of ISO 13374. Okay. If there is more question about standards.
No more question for now. And I would like actually to make a correction because every time I mistake Isadeus for BIBA, the company who coordinates the project is actually BIBA, which stands for Bremer Institute für Produktion und Logistik. So we have actually the coordinator connected. Sorry for the terrible mistake. It is Moritz, and I don't know if Moritz at this point would like to add something about his role or coordination of this project.
Hello, everyone. No worries about the mistake. We as a coordinator are very happy to lead this consortium with 3 very diverse use cases in this project, and with the same goal of having a predictive maintenance suite for them. And I'm very happy that we've had a good presentation of the first of the 3 use cases in this webinar. And I think it would be great if some of you could also join for the second and third webinar, so that you can see what the benefits of a unified predictive maintenance suite that can be applied to multiple use cases are. If there's any questions towards the project in general, I'm of course happy to answer some questions here as well.
Actually, I think that we don't have more questions. So yes, maybe we can wait just 1 minute more to see if anyone would like to ask you something specific.
Otherwise, you can find quite a lot of information on our project website, uptime-h2020.eu.
Yeah, that was actually I was about to add. I would like, I hope that you all enjoyed our webinar today, and I would like to invite you to join Uptime Community Partner Program. If you do that, you will be able to see our showcase events, webinar, industrial meetings, and we have also organized some expert workshops for the Uptime application partners. Joining the community is totally free of charge, and you will have the opportunity to benefit from new advances in predictive maintenance. And moreover, I think that's one of the main advantage of joining Uptime Community Partner Program, is that you will be actually able to get a free analysis from Uptime experts about the applicability of the Uptime platform to your specific application scenario. So here you have the link to our community if you wanted to join, and the link to our project website if you would like to have some more information. In the meantime, we have a comment, so just a participant thanking us for the meeting, so thank you very much. And very last, I would like to invite you to join us in the framework of the Hannover Messe, which will take place from 13 to 17 July 2020 in Hannover, of course. And there we are going to showcase our Uptime predictive maintenance platform. So thank you very much to all of you for taking part in the webinar, and I hope to see you soon.
Bye-bye.
Bye.
Thank you. Thank you.
Thank you. Bye.
Bye-bye.